Hello and welcome to part 2 of this introduction to learning from unlabeled instruction. In this video, I will present how we solve this specific learning problem by giving you intuitions of what our algorithm do. Finally, I will present results from simulated and online experiments using speech and brain signals as a modality. So let's start by a quick remember of the previous video. In previous video, we presented the motivation behind this work. We have identified the need for a specific engineered classifier in human-robot interactions, and have noted that if we want to send a robot in every home and have it adapted to each user's own preferences, it would require to train and to collect specific data for this specific user, which does not scale. So one way to tackle this problem is to build an adaptive classifier that can replace the need of the engineer collecting and tuning the classifier. To do so, we need to adapt automatically and online to each user. And I should remember that this classifier is used to teach the robot a new task, something that it does not already know, which opens the following questions. Can a robot learn a new task if the task is unknown and the robot is instructed using unlabeled instruction signals? We finally presented the kind of scenario we will consider in our research. So the task is sequential and requires to plan several actions ahead. The interaction protocol is turn-taking, providing signals in the form of a state, actions, and instruction tuple. And both the set of possible tasks and set of possible meanings are known. Finally, the instruction signals are represented as an n-dimensional feature vector. So in this video, I will give an intuitive explanation of our algorithm. As you may have noticed on our toy problem, after some interaction step, we can see a nice structure in the data. As we knew that the user was providing feedback type instruction, we understand that one of the cluster means correct and one of the other means wrong. So the idea behind our algorithm is to find which task best explains the structure of the data. So as we already know, the robot is aware of the kind of instruction the user is providing, in our case feedback, but also of the set of possible tasks the user may ask him, in our case going in one and staying in one of the 9 possible states of this grid world. Therefore, the robot can assess its own actions with respect to each task hypothesis. And by doing so, it can create artificial labels or artificial meanings for each task hypothesis and test the likelihood of the resulting dataset. So let's visualize what's happened in our toy example. So in this visualization, you can find on the bottom left corner of the screen our 3x3 grid world. Above are the instruction signals generated by the user. All the other graphs represent the task hypothesis. In our case, we assume the user wants the robot to stay in one of the 9 states, and we specially organized our visualization so that each artificially labeled data are organized as the grid world. For example, this bottom left square represents the imaginary label the robot will assess for the hypothesis that the teacher wants him to stay in this bottom left corner. Same thing for the middle square, will represent the hypothesis that the teacher wants the robots to go in the middle square of the grid world. So let's demonstrate the idea of assigning artificial labels for each task hypothesis. So if, for example, the robot performs the action going north, he will receive a new word, a new signal from the teacher, which will be represented in this 2-dimensional feature space. So it may be a data point here. And then, for each hypothesis, the robot will assign an artificial label that may be correct or wrong to this data point. So the action going north is correct if you want to reach one of the above states, if the goal is to stay in one of the above states. So you take this same data point and you assign a correct label for all the 6 top hypotheses. While for the 3 bottom hypotheses, you assign a wrong label. So that is the idea behind assigning artificial labels to points. So if we repeat this process for quite some iteration, we will see something very interesting happening. And indeed, if now I ask you which one of the 9 hypotheses is the more coherent, is the more likely to be the task taught by the teacher, you will certainly reply me that it's the top right corner. And you are right about this. But you use your eyes and the data are two-dimensional and highly separable. So how would you find this out without these visualizations? What we propose is to use standard classification techniques to train a classifier for each hypothesis and compare the final coherence of the classifier with the data. So let's look at an example. We can try to fit a simple Gaussian classifier. And you can see that the fitted model produces a high overlap between classes. And you can understand that the likelihood that the data point have been generated by the model is low. Whereas if you look at the correct hypothesis, then the Gaussian classifier looks more likely to have generated the data. And if we look at the global picture, we understand that this method enables to identify that the top right hypothesis is more likely than all the other hypotheses. The algorithm is as simple as this. Of course, when we actually implement it, we can use a probabilistic version of this, and if you want more details about the implementation, you can refer to our publication on this topic. So this example is a toy problem, and we tried our algorithm in more complex scenario. So in the first scenario, we consider a simple pick-and-place task, where a 6 degrees of freedom robot equipped with a gripper can manipulate 3 cubes, which can stay at 4 different positions and create a tower of at most 2 cubes. So to represent the problem, we used a Markov decision process. And the one we use has 624 states, which will be our set of hypotheses, meaning that the teacher wants the robot to reach one of the 624 possible combinations. To do so, the robot have 4 possible actions, which are go left, go right, grasp a cube, and release a cube. So to teach the robot this task, we will use real spoken words that will be mapped to a 20-dimensional space. And in this kind of setup, we can identify 2 sources of noise. The one due to the speech itself, because words are never spoken the same way, and importantly, the noise from teaching mistakes, where the teacher may erroneously assess the robot actions. So the interaction may look like this. You have a robot that is performing an action, grasping the blue cube. And then the teacher is providing a feedback signals, in this case, a yes. This feedback signals is recorded using the microphone and mapped to a 20-dimensional feature space. And the robot do another action, receive a new signals, and we repeat this process again and again. And after several iterations, we can ask the robot to do what he understood, and he can repeat the correct task. So if we look at simulated experiments of this exact same setting using real recorded speech as teaching signal, we can see that in 200 iterations, the robot has identified the correct task. Those curves are tracking the probability of the correct task. We can do this because we are outside of the system and we know what the teacher is teaching to the robot. So we can track the probability of the correct task. And it's going up, and at 200 iteration, it reaches 1. That means that the goal hypothesis have a 1 probability, and all the other 623 has probability of 0. That means we identify correctly the correct task. And we tried this with 2 different kinds of teaching signals. Feedback in green, which are the teacher assessing the robot action as correct or incorrect, and guidance in blue, which is a teacher telling the robot what to do next, like grasping a cube, releasing a cube, going left or going right. And interestingly, it takes more time for the guidance case to reach high probability, whereas the information it receives, the robot receives, is more rich and more complete. The robot does not have to test each possible action to know if it is good or bad. But in the kind of problem we have here, where the instructions are unlabeled, we need to identify from the data 4 categories for the guidance case, which are the name of the actions, and only 2 for the feedback. And therefore, doing the guidance requires more data to identify the clusters in our feature space. Another very interesting feature is that once the robot understood a first task with high confidence, so that is a red curve here. So this is a real experiment done with me talking to the robot. It's not a simulated. So after 100 steps, we reach a quite okay probability for the correct task, and we can stop the learning and freeze the assigned labels to this particular hypothesis and start to learn a new task from this classifier already learned. And for sure, we are going faster this time because we know how to interpret the signals. So we further apply this algorithm to a different and more complex sources of signals. In this second experiment, done in collaboration with Iñaki Iturrate and Luis Montesano at University de Zaragoza in Spain, we were using error potentials which are in the brain. And those error potentials are assessing the actions of an agent in a grid world. So error-related potentials are linked to region in the brain that activates when observing correct or wrong events, which is perfectly suited for our algorithm. And what is very important here is that the algorithm is exactly the same as in previous experiments. We just give different input signals. We do not need to run a long and fastidious calibration procedure. Our system will adapt automatically while the agent is trying to perform and understand the task. So while the data here are noisier than in previous experiments, because they are brain signals, the possible task was reduced to 25 in this 5x5 grid world. So we performed online experiments and observed that for all subjects, the system was able to identify the correct task in less than 150 steps. So we are now at the end of this video, and at this point, you should understand how we tackle this problem and what is the principle of our algorithm, as well as the kind of setup we successfully applied this algorithm. So in next video, we will discover and solve a very important challenges. We have seen so far that with repetitive interaction, we are able to learn a task from unlabeled instruction. An important feature is that the robot is kind of leading the interaction. Indeed, by its actions, the robot can trigger different instructions from the user. And if we look at different action selection methods, such as random, here in blue, and epsilon greedy here in red, we can see that the performances are affected. So the naturally arising question is therefore, can we do better than this? Is there an optimal strategy? And that will be the topic of next video. So thanks for watching and see you on next video.